Hello everyone, I'm Vishal Zinjuvadia from 410 Networks. I'm here to discuss TraceFlow. That is the agenda for today's discussion. We will start with a motivation for this protocol. We will discuss how network designs have evolved over time to basically satisfy the requirements of the applications that use these networks. We'll specifically focus on the needs for resiliency and redundancy, which has caused operators to use more and more link aggregation groups and ECMPs in their network, which is all good, but what has happened is the OAM tools have not been able to keep up with these changes in network designs. And as a result, what happens is these tools are not effective as much as they are on a regular network in giving us information about why a problem happened or for any other reason that they are used for. We'll dive into the problem statement. We'll go through what enhancements we feel that we can do to these protocols. We'll go over basically the different network types that we can address, even though we'll be focusing on IP networks only in this discussion, which is basically what the protocol's initial focus is, but we'll discuss how it is extendable to other network types. We'll go over a use case scenario which will help us put all of that together. It will show a typical application using link aggregation groups and ECMP. It will show how it is likely that an OAM tool that we use, such as a ping or trace route, can take a different path than what data traffic would take. We will also go a step further. We'll find out what additional information we can benefit from that is not available today. There have been some developments in that area, which is actually a great thing. We feel that there is a disconnect though, and basically this presentation is geared towards that. We come to the most important section of this discussion then. We'll discuss, so armed with whatever we would have discussed by then, I will go over why I am here, what is the purpose of this presentation, what do we intend to take back from this discussion. That's basically the key point that I'm here to basically highlight today and take your opinion on. We'll go into TraceFlow protocol operation. We'll go over a basic mode of operation. We'll go over an advanced mode of operation, which opens up a lot more applications. We will also basically go over the important message types we use in TraceFlow. However, this is not going to be a detailed discussion on the nitty-gritty of the protocol. We will go over enough material to help all of us familiarize with what the protocol does. There are a few issues with the protocol which are in somewhat fluid state, which are either open issues or issues that we have taken a stand on or have an inclination towards, but are not necessarily the best way to do it, and that's basically where we need your feedback. Basically, if you have any opinion, if you have experiences that helps us, that's basically the idea of going over the open issues and some of the decisions that we made. And then we'll go for question answers and any other feedback that you have. So as we discussed, today's networks have evolved into complex heterogeneous entities. Use of link aggregation and ECMPs is more prevalent, and it's for a good reason. It's to add resiliency, to add redundancy to the networks, which is all fine. However, what that has done is increase the gap between what the OAM tools like ping and traceroute were designed to troubleshoot and what is requirement from an OAM tool today to troubleshoot a problem in the network. Some of the tools we use are destination address based, which does not work very well when you have equal cost multipath, when you have link aggregation groups, when you're troubleshooting a network issue. There are many cases where flow-based information is used to forward the traffic. Again, another point where OAM tools like ping and traceroute don't help us very much because they are destination IP address based only. Other than that, as I discussed earlier, it would be great if along the way that the control packet or the OM packet, when it goes through the network along the path that the data would have taken, it collects information that is relevant to debugging the problem. And I'm not talking about dumping your entire register set or dumping all the counters that you can think. I'm talking selective information which the operator has control over. We feel that there is value in being able to specify the information and collect that along the actual path that a traffic flow would take. Again, the need comes from our customers. We have discussed this idea with them, and so far the feedback has been positive. It is in a very early stage, this protocol, and while we worked on it, we were very excited, at the same time a little puzzled. We were excited because because we are doing a new protocol, like with every new protocol, there's a lot more that we could do because it's a whole new ballgame, and you put information that you want there, you have that liberty. But we were a little puzzled because things that we did not think are really important ended up making the protocol more complex, a little bit more complex than ping and trace route. And we actually had to stop ourselves from doing any more analysis and design on it. What better group to talk to than NANOG to come and get your opinion on whether this is the right direction, whether you feel the issues we have left out are of important enough to make the protocol complicated, and some other open issues we will discuss. So briefly, the problem statement. Need an ability to trace 3-5 n-tuple flows through a network. Need to find the exact physical path that a user-specified flow would take through the network, and selectively collect information along the way. Now, clearly when we are adding more details, more data to any protocol which goes through the network, it is important to include security information. It is important to protect it. So there is a security angle to it, which we won't go into much detail here. I will discuss the location of the document that discusses all of this. That would actually be very useful, going through some of those details and seeing whether all of that is really justified or is it just too much. Of course, we would like to extend it to other network types. We are going to focus on IPv4 for now, but it can be extended. It is designed in a way that it is extendable to other network types. A very good document to read through is a requirements document that actually lists several requirements for both link aggregation and equal cost multipath type networks. This document goes into requirements for devices that do switching on packets along those two constructs, lags and ECMP, or even routing on those. So it actually does a good job of spelling out the requirements. This document also discusses inter-AS requirements. Some of them, that's basically an area that is still too far. We have not even reached there, but this document does a good job of spelling out the requirements for intra-AS and inter-AS behavior for this protocol. So this is a use case document. This is a small network. It's expected to be a representation of, it includes all the different constructs we want to. It is a way that we will highlight why current ping and traceroute protocols may not be able to help out in situations where link aggregation groups and ECMPs are heavily used. So there are 4 routers here: RT1, RT2, RT3, and RT4. RT1 has been programmed to use the link aggregation group 1 and the physical link between RT1 and RT4 as an ECMP candidates. Traffic would be equally balanced between the two. RT2 has another lag that goes to RT3, as you can see. Let's assume for a second that the data traffic actually takes the green path, the green arrow. the one that is below lag 1. It is entirely likely that the ping and the traceroute packets that are originated on RT1 do not take the same component link or the component lag members as the data would have taken, or doesn't even take the lag at all and uses the physical link to RT4 to actually reach the destination. So the red lines here show the probable paths, and this is not all the paths. Ping, again, this is again likely scenarios. It is likely that ping and traceroute will take the actual path that the data would have taken, but it's all probabilistic, and it depends on the implementation of the device that does the hashing on it. But again, since ping and traceroute are destination IP based only, and the flows could be routed or switched based on 3-tuple, 5-tuple, or any other n-tuple algorithm, it is likely that there is a disconnect. So as you see here, on the lag between RT2 and 3, there is a soft failure on the component through which the data is actually going through, which means the data is affected. Now when we get that report and we do a ping and a trace route, as the red lines show, it is very possible that the ping and the trace route will take the other component member or other physical interface and completely miss the link that has a soft failure. In this case, we would not detect a problem, whereas the data would actually be blocked or would be dropped or whatever, maybe corrupted, depending on the soft failure that is there on that link. So what is the objective? With the information we have so far, traceflow, which we will be discussing in some detail in the following slides, is our proposal or our approach to solve some of the problems we have discussed so far. We have designed it to be extendable to future needs, including other requirements which we have not touched upon yet. It is extendable, and we can already foresee some more applications beyond troubleshooting that it can be used for. It has been presented in one of the ITF working groups. The URL is shown there. It has the latest copy of the draft. We are working on updating it with some review comments we received, but it pretty much stays, the concept behind the whole protocol is still whatever the document talks about. What we are looking for is your feedback, your thoughts on what we are going to discuss. Actually on thoughts about everything related to, or anything related to this whole problem, the problem statement, the approach we took, the scope we defined, and of course, there are open issues we will highlight, and if you have any opinion, feel free. That would actually be very useful for us. So again, the green line here on this diagram shows the data flow. The way the protocol works is it sends out request packets, which are denoted as TFRQ, trace flow request packets, and each device along the path that receives this request packet actually returns a response packet, which is denoted by TFRSP, trace flow response. How does RT1 know which component link to send the packet on, to send the request packet on? RT1 basically implements a way to determine, given a particular flow which the operator would have specified, and there is another, you could actually determine the flow by providing a packet itself to the application. The application would determine what part of the packet constitutes a flow for this device. So that RT1 would run the specific hash algorithm or whatever forwarding algorithm it would have used to forward the data flow on the flow that the user specified, either typing in the 4 or 5 tuple information or providing a capture of a packet for that particular flow. Either way, when RT1 gets that flow information, it runs a forwarding algorithm on that flow as if it would be routing or switching it, and determines the egress path, egress component link or the egress physical link that the packet would have taken, sends out the request packet along that link to the next hop router. It also carries a lot of other information. We will go to that in a few more slides. But RT2, when it receives a packet, it can rest assured that the data packets for that particular trace flow request would also have come on that component link. So with that input interface information and whatever n-tuple information RT2 has been programmed to use for routing, RT2 can establish an egress port for that trace flow request. It treats that request as if it was a data packet that came to it on that interface. A lot of implementations use the incoming interface also in determining the egress interface. So RT2 knows which egress component link the packet should go out. It would send it out to RT3. What RT2 would also do when it forwards it to RT3 is it would send a response packet back to RT1. RT1 would have been specified as an originator in that packet. Optionally, an originator could be a third-party device, a laptop, or any other device on the network. But for this specific slide, we will assume RT1 is the originator. So RT2 sends the response back to RT1 while it forwards the request along the next hop interface to the next hop router. RT3 does the same, basically processes the request packet and determines the egress port, which we don't go into that in this slide, but it sends a response back to RT1. So RT1 becomes this, RT1 starts collecting all this response packets, which has valuable information that it can use to do some calculations on, make some inferences based on it, and basically this helps the operator determine, first get the information which he or she is interested in. Could be input counters, could be input CRCs, could be ACL drops, could be any information. The operator at RT1 or on his laptop looks at all this data he is getting along the actual physical path that the data flow would have taken. And hopefully that is going to help the operator determine the cause of the problem or maybe further his debugging efforts. This is an advanced mode of operation. In this specific mode, the purpose is not just to debug a network problem. The purpose is basically to determine all possible physical interfaces or logical interfaces through which a data packet would take or through which the data packet would go. And here we are only going to focus on the destination IP address of the data packet. So this diagram will actually make it clearer. It did not come out right, looks like. But RT1 would be requested to determine all the physical paths through which, let's say, any packet to a destination IP address of some destination IP address, any packet where the source IP is unknown, the layer 4 protocol is unknown, only known component is the destination IP address. RT1 is determined to initiate that search for physical or logical interfaces throughout the network where a destination IP address would go. It would send out multiple request packets, one on each component link or physical link through which it would hash a packet for that flow. Again, it only considers the destination IP address, which is why we see multiple packets coming out of RT1. So if you look at the diagram, RT1 actually sends out 4 packets, 4 trace flow request packets, 3 on the 3-member lag between RT1 and RT2, and 1 on the physical link between RT1 and RT4. RT2 receives the 3 request packets. It realizes the purpose of those packets, consolidates into one that it processes, and sends out to RT3. And again, because it is destination IP-based forwarding only, it goes out on both of those lag members onto RT3. And RT2 sends its responses to RT1. Now, an observation here could be, why can't RT2 bundle up all those 3 response packets into one packet and send it back to RT1? Why does it have to send the 3 of them individually? We have designed this protocol to be stateless. We would not like any of these routers to maintain any state about any of these queries coming in. As a result of that decision, RT2 would send responses as it receives those requests. But the packet that it forwards to RT3 will be the one that it receives on its designated primary member of that lag. So the idea is to keep the protocol stateless. So again, you see a lot more blue lines in this diagram than the one before, clearly indicating a problem that there are too many control packets floating around, and that with this could clearly cause a lot of information being sent back to RT1. Again, this is an advanced mode of operation. This is not something that I think would be used without understanding what it means and why it needs to be run. However, however, we feel that in a closed environment, in a smaller network or within your administrative domains, within certain areas of that domain, it might help running this to determine what physical interfaces or logical interfaces a particular particular destination IP would take, just to make sure it's behaving the way you want it to behave. It's not taking any circuitous route through somewhere that you don't expect it to take. So that's basically it on this slide. Information is sent back. The only difference being it exercises all the data paths that a flow would take. Some of the message types and its contents. There is a request message, as we discussed, and a response message. Primary component being the flow descriptor, which is nothing but the first n number of bytes of the packet. We feel 256 bytes would do it. An easiest way for it to be generated would be capture a packet of the flow that you want to debug and put that packet in this TLV. That is basically the flow descriptor TLV. We also have a way to specify any flow related information. For example, this flow the packets for this flow should never be fragmented. If that is a requirement, then that processing also happens on all the transit devices through which the request goes through to make sure that the egress interface meets the criteria for that fragmentation requirement specified. Clearly, the originator address is important. You would want to send data back to the person who requested it, who originated all of this processing, so that that entity has the information has all the data to munch and then can make a decision of what is going wrong where. Termination TLV discusses basically you don't want this packet to go out of bounds, go into the internet, go places where you never imagined for it to go. Or maybe when you are doing the advanced mode, the fan-out mode of operation, you only want certain routers to be there who should send information back to you. Termination TLV is a way for you to do that. Again, I'm not going to go into too much detail on the messages. The document that I'm going to share with you has all that information, and it discusses all of these all of these message types and the contents in detail, and gives a reason of why we have it there. Requested information is interesting. It allows the operator to specify what pieces of information it wants from each transit device. So that is, we feel it is important not to get a dump of everything on each of the transit devices and make it an unmanageable task, but to be able to specify, I only want CRC counts, I only want, it could be any of those SNMP OIDs that we manage. And we only get selected information along the data path of the packet. Authentication is again very critical. As we add more data to the protocol, we want to authenticate it. That is the purpose of that TLV. Response packet looks a little bit like the request. It has a flow descriptor. It includes a bunch of other TLVs. Basically, the encapsulated packet mask specifies what portions of the data packet that transit device used to hash it or send it out on the egress port. And this could be very different from one router to another, depending on the implementation configuration. So you would want to know whether RT2, RT3, or any transit routers, what part of the packets they used when they forwarded the request packet to the next hop router. A record route would, again, as the name suggests, would record the route through which the request packets goes through. It helps very much in an event of a link failure where you never hear from any router beyond a certain link or a certain router, and at least you know the actual path that it took. It also helps when you miss occasional responses from these transit routers. Interface info TLB, as it suggests, is information about the interface. The result TLB shows whether the processing of that packet, of the request packet, was successful on the transit devices. It has a lot of very interesting result codes. An example of it would be this flow that you are requesting to be probed is going to be dropped on this router because of an ACL policy or any QS setting. So this is again information that is very confidential, and the use of this should be within the domain. I don't want to go into all the security implications, but this is, I think, a very, very powerful tool that could help us in the initial stages when we are bringing up a network to detect ACL policies that should not be there or are not configured right. There are many other result TLB, many of the result codes in the TLB. The document has all of that information too. So moving on to, so actually so far is the protocol operation, giving everyone an idea of how it works, what is the scope of the protocol, what we have chosen to fix or to implement. Moving on, this slide talks about an open issue that we are not sure what stance we should take, and this is presence of devices that do not support this protocol along the way of the data packet. Legacy devices. Clearly, there could be devices that get this request packet that don't know what to do with it. That again in itself is not a big problem. The problem is that that particular device would forward that packet further using the destination IP address on it, and it may not actually go in the direction that the data packet that it is trying to probe would have taken. So not only it doesn't include the information I'm requesting, the legacy device, but it actually sends it out in the direction that is not the direction through which the data would have gone. So that is a bigger problem, we think, and hence it is unclear whether we have thought about several different ways to try to fix it, but again this is one of those things that may seem simple, but it actually makes the protocol really complicated if you want to work your way through the legacy segments of the network. You cannot expect on day one to have complete support for this thing in your entire network. Your portions of the network may be upgraded at different times. So what do we do with legacy networks is basically a question that we have. One couple of solutions that we had is use a probe packet that looks exactly like the flow that you are debugging. So the trace flow request packet, essentially the header on it would look exactly like the data packet that you want to debug. This way, even if it hits a legacy device, it would route that request packet in the same way that it would have routed the data packet. So if we do that, and if we add a mechanism for each device to identify its trace flow capability, we can work our way through the legacy segment. We can determine the right data path through the legacy segment, and we can also determine, we can also get information from all the devices that are trace flow capable across legacy segments. The problem with that is when we make the probe packets look like the data packets, they would become indistinguishable from data packets, and you would not be able to separate them from the actual data, and that's a big problem. You would definitely want to limit your control traffic, and you would want to limit your control traffic by the application. Your ping, your trace route, all these can be identified. Problem with making the probe packet look like data, which helps on the legacy segments, again, is it's indistinguishable from data. You cannot control it. So it's actually going through the network that is taking the data traffic also, and it's using up your bandwidth, and there is no way for you to control it. Other risk is the probe packet now, which is looking like the data packet, may actually make its way all the way to the end node for which the data packet is destined into the application, and God knows what would happen if the application receives this probe packet. There would be problems in that area too. Again, clearly we can handle it. A potential solution, like we discussed, is basically make it look like data and then use trace flow capability detection and find your way through the legacy. But again, the protocol becomes very complex the moment we try to do that. So we decided, let's stop, let's step back, let's think whether, and we understand it's likely that legacy networks or legacy segments will be there along the path that the traffic would take. But again, the cost that you have to pay to make it work with legacy seems very huge. We are exploring other ideas, and there may be other ways to do this, but we just want to have a general sense of whether that's direction we should continue to march on. Is legacy support something that we cannot live without? We have to have legacy support, even if it means complicating the protocol. I mean, we may be able to make sure that the probes are distinguishable from data. There may be some solutions in that direction, but like I said, we decided to step back and see whether this is worth it, going in that direction. Another open issue is encapsulation. Currently, we are suggesting the use of UDP, but again, we are not 100% sure that is the way to go. There are implementations that may not be able to handle it well. It may need certain changes in certain code sections that are sensitive and are not are better left untouched. Still, UDP comes out as a simple way to identify this protocol, and we, at this point, we have proposed that in the document. However, it is likely that we may end up using a new IP protocol type, or an ICMP message type, or outer alerts, or any other ways of basically terminating the packet at each transit device. The idea here is to be able to terminate the control packet on each of the transit devices. So that's an area that we have taken a stand, but we're not, it's in a fluid state. We are not 100% sure that is the right way to go. Again, this is a very early stage for this protocol. We feel there is a problem. We would like to hear from you whether the problem is real, that we have identified the scope correctly, and whether we are in the right direction in terms of adding complexity to existing OEM tools to get the information that we are looking for. So again, these are the open issues, and there are many others in the document. That's it. Unfortunately, this version of the slide does not have the link to the document. I will have that updated. It's basically, again, in the ITF repository. It's actually, there you go. There it is. There is the document. And it has a lot of other issues that we have considered, we have taken a stand on, or we have an open question on. The appendix actually lists a lot of decisions we have taken, why we have taken them, and maybe some open questions that we have that we need to address at some stage. However, the document is very complete in the sense it discusses the core concepts, it discusses the approach we are taking, and we have a list of objectives from the protocol that we are able to achieve using the protocol definition. We are hoping to be able to get feedback from the community and be able to close on the open issues, be able to solidify our stand on the ones where we are not so certain, and any general feedback on this topic would help.
So just a brief message from the PC. The break is now open if anybody wants to go, and if anybody wants to ask Vishal questions or discuss, suggest stuff, then by all means, please do so. This is what it's about. People are trying to come up with a new protocol, and if you don't speak up, you may not get something usable.
Hi, Richard Steenberg and Inlayer. So I definitely agree with the need for something like this. We see on a regular basis a lot of problems with lag paths where you have 8 paths and you're running a trace route and you may only be hitting 3 of those paths, and one path has packet loss somewhere and you don't know about it until some customer says, I can load slowly every 8th website, what's going on. So it sounds like a good concept. I'm not sure about your implementation though. It seems like It seems like there's two things you're trying to focus on. One is detecting which path you're going over, which it seems like the easiest way to handle that, and this would scale to outside views of your network as well, is to just do an ICMP destination unreachable extension where you say, this is the fourth path out of an 8-member lag. And that is public enough information that could go out to anyone that has traceroute anywhere on the internet, and then they could help determine what the problem is. And then the other problem that you're trying to troubleshoot is almost like a source routed pick the lag packet, and it kind of seems like either by doing something like that or by doing a tree packet that expands everywhere, both of these solutions seem like a bad idea compared to just having the router, have each router as part of a layer 2 OAM, have it do the probes over each one of the paths, make the results available via SNMP, and then you just go SNMP query your router. Because it seems like you'll never be able to actually hit every one of your paths from some central control box somewhere that's trying to do a trace route through every possible lag that you might have.
Okay.
Richard, what about layer 3 O&M? We're going to create that too?
Say that again?
So what about layer 3 CMP?
Well,
Okay, thank you.
Mike Hughes links. There's many different ways to sort of skin this cat, really, but it's a very real cat. So I can't believe everybody's sort of sat here going, looking into their laptops unless they're just running out of sugar from lunch. But who here? Raise your hands. Do you use lag in your network? Yeah. God, not that many of us. Wow. Do you use ECMP in your network? Keep your hands up. Raise both hands if you use both. So there is this going on, and there is a real need to find this stuff. I know that if I had tools like this, I would have found my life in the last 2 months a hell of a lot easier. Because I was looking for needles in haystacks. So, I think the main thing is go read the draft, come up with suggestions, and feed into this stuff. Because we really need this stuff, because otherwise, you're looking at an IP packet that's going over ECMP, over lag, with some MPLS wet string in the middle, and you are screwed if you're trying to find something wrong with this. This is about making your life a hell of a lot easier, and I really like this. You've just got to go and get more people, get them feeding back into this so stuff actually happens.
Thanks. Thank you very much.
I'm Igor with Yahoo, and I just want to echo what Mike is saying. We have a lot of ECMP over lag. Sometimes it translates to 64 paths in the end that you've traversed. It is like looking for needles in a haystack when you have problems and stuff like this. You may not care about it now. You'll care about it 3 years from now when 100 gig isn't ready yet and you're doing insane amount of lags. Now is the time to bring it up, because by then it'll be too late.
Thanks, Igor.
Joe Myman, just wanted to clarify what kind of scope we're looking at. Something that can be usable end-to-end through other people's networks, or something to be used inside a network that you plan on owning and controlling?
Very good question. So the original intent, short answer is both. However, the information that we are requesting could be sensitive outside of the network, and so there are multiple different ways to make sure that only the public information, or only information that is okay to send out publicly, is sent out of a domain. We have suggested a couple of security mechanisms to do that. However, what we are doing is within a domain, you can specify a list of parameters that are okay to send out, and you identify the routers using their ID and the security information that is embedded. And outside of a domain, you severely restrict the information that you send out in response to this packet, enough that helps the querying guy know what might be wrong, but not anything more than that. So a typical implementation is traffic goes through 2 service providers, and there is a problem in service provider B's network. Service provider A is doing some troubleshooting, and it can determine, hey, provider B, I think the packet may be getting blocked because of CRCs in certain segments, or maybe because of oversubscription. Can you take a look? So there are ways to determine what is okay to send out and what is not okay to send out. And with security mechanisms we have, we feel that that can be achieved. So answer is again both type of networks.
So you're saying that you want to delineate that for packets that leave the administrative domain, only enough information that you can hand off to that AS and say, can you please look at this and further develop the troubleshooting?
That is our intention. We feel that that might be the most preferred approach, but if you have other thoughts, if you have an opinion either way, I would love to hear.
Thank you.
Thank you.
Hey, Vishal.
Hey.
Louis, Equinix. So an interesting way to use this could be that an exchange provider, especially if it's a distributed exchange, can use it within their own network, and also at the same time the ISP endpoints for that exchange can run it on a different domain to see if the exchange provider's network is messed up, just to troubleshoot any packet loss you might have.
Thank you.
Oh, there we go. So yeah, Danny McPherson. So I was just going to mention, I know you had a pointer in there to Shane Amonte's draft that myself and folks from BT and a couple other places are co-authors on. And that's actually a requirements document to help specify protocol or solutions mechanisms, sort of under the ITF framework. So if folks are interested at all and questions like the previous one about sensitive data being exposed and what are the different contexts this things will be employed and what are all the different mechanisms that need to be provided and so forth, then I recommend that you grab his slides. He does have a pointer to that draft there, and provide feedback to the authors or to the ops or internet area in the ITF because we want to move forward with this, but to make sure we capture all the requirements correctly is really important. And this is certainly goes a long way towards specifying some of the solutions. So, thanks.
Thank you very much. Okay. Thank you everybody for being here, and thanks to the committee for letting me present.
All right, thanks.